Good morning, ladies and gentlemen. I'm Pietro Gucciardi from the National Council for Research, Institute of Chemical Physical Processes in Messina, Italy, and welcome to this first lecture on the introduction to Raman spectroscopy. The first part will concern vibrational spectroscopies, namely infrared and Raman spectroscopy, and then we will discuss the classical theory of Raman, then we will show some experimental setups, and we'll conclude with advanced aspects on quantum theory of Raman spectroscopy. So, what is spectroscopy? Light, as we all know, is a probe of the molecular structure of matter. When light is absorbed, molecules go to an excited state. The excitation of the molecules provides emission of light by the molecule, as we can see in this small cartoon here. The spectral analysis of the absorbed emitted light is what spectroscopy is, and it provides information on the energy levels of atoms, molecules, and solids. Light spectroscopy can be carried out in the visible, ultraviolet. In this case, we have information on the excitation of valence electrons. Can be made in the infrared, and then we provide information on the excitation of atomic vibrations in molecules and solids, and this will be the objective of our lecture. Otherwise, we can perform spectroscopy in the microwave range, in which we just excite rotations of the molecules. In this cartoon here, we can see the different ranges and wavelengths at which these three kinds of spectroscopy occur: visible, infrared, and microwave. So, what is vibrational spectroscopy? At temperatures higher than zero, atoms in molecules and solids do vibrate. We can see this in these two pictures. Spectroscopy of the vibrational energy gives information on chemical structure, conformation of compound, presence of specific compounds in unknown samples, properties of the chemical bonds and interaction of the compound with environment, electronic structure, formation of new species during chemical reactions, and information on the structure. An example of what can be measured with Raman spectroscopy is given here. This is a map of carbon single-walled nanotubes deposited on silicon. If we acquire a Raman spectrum, we typically end up with several features that can be correlated and provide information on what is present on the substrate. For example, these three peaks here, this one, and this band, are related to the presence of the substrate, silicon. If we look at these other modes are instead related to the presence of carbon nanotubes. And in particular, this RBM mode is related to the diameter of the carbon nanotube. Its energy is dependent on the diameter of the carbon nanotubes. The D band provides information on the electronic and symmetry properties. For example, we can understand if this nanotube is metallic or semiconducting. And the D and the G prime band are typically of morphological properties, provide information on morphological properties and basically on the presence of defects. Let's have a look at the quantities and units that are used in vibrational spectroscopy. Light energy is typically characterized by different quantities. This can be the energy measured in electron volts, the frequency measured in hertz, the wavelength measured in nanometers or in micron. The constitutive equation is this one, in which the energy turns out to be proportional to the frequency through the Planck constant, or inversely proportional to the wavelength through the speed of light and the Planck constant. As a rule of thumb, we can calculate the energy in electron volts as 1240 divided by lambda in nanometers. Electronic transition occur in the so-called visible range, that is between 400 nanometers and 700 nanometers. Vibrational spectroscopists use a different quantity to measure the energy, that is the wave number. The wave number, expressed with nu tilde, is the inverse of the wavelength of the radiation measured in centimeters. So, nu tilde is measured in centimeters to -1. As a rule of thumb, we can calculate the wave number in centimeters to -1 just dividing 10 to the 7th by lambda in nanometers. To give some examples, a radiation with a wavelength of 10 microns is equivalent to an energy of 1000 cm to -1. Radiation of wavelength 2.5 microns is equivalent to a radiation of energy 4000 cm to -1. Vibrational transitions occur in the infrared between 10 centimeters to -1 and 12,520 meters to the -1. The easiest case we can study is that of a diatomic molecule. Let us consider a system in which we have two masses at position x1 and x2 that are linked by a chemical bond that is modeled as a spring with spring constant K. As we know, the movement of this system can be separated between a movement of the center of mass plus a movement relative to the center of mass. The equation that rules the movement of the center of mass is m d2x over dt squared equal to 0. It means that we have no forces, so the molecule is free to move at a fixed velocity v0. If we put our attention on the relative movement, instead we have the equation of an oscillator, of a harmonic oscillator, in which mr is the reduced mass and k is the spring of the constant. Q here is x2 minus x1. If we solve this equation, of course, we come up with an harmonic solution, q equal to q0 cos of 2 pi nu vip t, where nu vip is the vibrational frequency that is proportional to the square root of k and inversely proportional to square root of the reduced mass. So these two mass will oscillate at a typical frequency that is given by this expression. And the movement of all the system can be divided into a translation at constant velocity plus a vibration at the natural frequency nu vip. Let us now investigate which are the vibration energy levels. Let's start with the classical picture. As we can see here, in the classical picture, the energy potential is proportional to the square of the position of the particle. The energy is equal to the kinetic energy plus the potential energy, and this is a constant, and is proportional to the squared of the displacement of the particle. What is interesting to note is that the energy is 0 when Q0 is 0. Another thing is that the energy spectrum is continuum, and another important thing is that vibration is confined in the parabola Q smaller than Q0. Okay? This does not hold in the quantum picture. In the quantum picture, we have to solve the Schrödinger equation, in which we have to determine the spectrum of eigenvalues of the energy and the wave function. The wave function is a property of the particle whose square modulus is proportional to the probability of finding the particle at a position q. Okay? What is important to note is that when we solve the Schrödinger equation, the spectrum of vibration E of n is proportional to the frequency, vibration frequency, and it's discretized. As well, we have a discrete number of eigenfunctions that are proportional to the Hermite polynomials of this quantity. What is important and what is different with respect to the classical picture is that now the 0-point energy, that is the energy when n equals to 0, is no more 0. But there is a 0-point energy that is different from 0, and it's 1/2 h nu vip. Okay? And another important thing, of course, is the energy spectrum is discrete. The levels change by units of h nu vip. And finally, that the probability that q is higher than q0 is non-zero. Okay, so the wave function somehow comes out from the potential parabola. And this indicates that if we have another potential closer here, there is a zero probability, there is a non-zero probability that the particle tunnels from one parabola to the other. So far, we have described the potential as an harmonic potential. Actually, the potential that describes the binding between two atoms in a diatomic molecule is not harmonic. It has some specific shape, as you can see here, in which locally can be approximated as a potential, as an harmonic potential, but actually is well described by what is called Morse potential, in which which has this expression in which this dE is the dissociation energy. Basically, it says that if we excite the system with enough energy, we will dissociate it. So the dissociation energy is described by this potential, where beta is proportional to square of Ke, and Ke is the force constant at the minimum potential. There are some differences between the two potentials, and the main are the following. In the harmonic potential, we have seen that energy is quantized, but all quanta have the same intensity, h nu v. While here we have some correction factor, as you see this term here, that makes the vibrational level no more equally spaced, but with a spacing that decreases as n increases. N is the quantum number describing the vibrational energy. Okay, so while in the harmonic potential we have all equally spaced level, here the levels are no more equally spaced. So far we have seen that in a diatomic molecules we have a single vibration frequency. What happens to polyatomic molecules in which we have more than one atom? If we assume that a molecule has n atoms, associated to each atom we will have 3 degrees of freedom, so in total we will have 3n degrees of freedom. From these 3 will be associated to the rigid translation of the molecules, and then we will have rotations. If the molecule is linear, we will have 2 angles, and so 2 degrees of freedom associated to rotation, while for non-linear molecules we will have 3 degrees of freedom associated to rotations. The number of degrees of freedom associated to the vibrations will be the difference between the total number of degrees of freedoms minus those associated to the translations and to the rotations. So we will have 3n minus 5 degrees of freedom associated to vibrations for linear molecules, and as you can see here, for a CO2 molecule that is linear, we have basically 1, 2, 3, 4 vibrations, while for non-linear molecules the number of degrees of freedom associated to the vibrations, and so the frequencies associated to the vibrations, will be 3n minus 6. A typical example is water, that has 3 atoms and has 3 vibrations, 3 distinct energy of vibration. Associated to each degree of freedoms there is a vibration, and associated to each vibration there is a so-called normal mode. In each normal mode, all atoms of a molecule move with the same frequency, nu k, and they move in phase. The atoms move simultaneously around the equilibrium position, while the mass center remains unchanged. The vibrational amplitude of the different particles can be different. To each vibration we associate a normal coordinate, and the behavior of the normal coordinate will be harmonic, oscillatory, with an amplitude qk small, an equilibrium position q0k, and an associated vibration frequency nu k. The normal vibration typically do not interfere with each other. There is a so-called orthogonality principle of the normal coordinates. The normal vibration typically have different frequency nu k. So if we excite the system at a single eigenfrequency nu k, this normal mode will be excited and no other ones. There are different types of vibrations. There are vibrations that cause a change of the bond length, that are called stretching modes. This is a typically symmetric stretching mode, and this is a typically asymmetric stretching mode. Okay. There are other vibrations in which that change the bond angle but do not change the bond length, and these are called bending modes. And among the bending modes, the most important are the in-plane bending, scissoring, in-plane bending, rocking, out-of-plane bending, wedging, or twisting. We have seen that vibration occur in the infrared. We have the first part that is called far infrared, between 10 and 200 centimeters to -1, in which we have typically radiative oscillations of crystals or amorphous solids. Two typical examples are the radiative breathing mode, the respiration mode of carbon nanotubes, or the shear mode in 2D layered materials in which one layer moves with respect to the other. This is typical 200 centimeters to -1 is typically KBT, where T is the ambient temperature. When we move forward from 200 centimeters to -1 to 4000, we have all the fundamental vibration. This range is called the mid-infrared. Furthermore, we have the so-called near-infrared between 2.5 microns and 800 nanometers, and here we have all the overtone and combinations. So instead of having one phonon mode, we have two vibration, three vibration at the same time. The mid-infrared is by far the most important and interesting region. Here we have all the different structural elements in which the vibration of the functional groups double bond, single bond, triple bonds occur, and as we can see here we have a map from 650 to 4000 centimeters to -1. We have here at lower energies CC single bond, here CC double bond around 1600 or 1700, and what is important to note is that since the frequency is proportional to the square root of the constant of the oscillator constant, stronger bonds correspond to high frequency. As well, since nu is inversely proportional to square root of mu of the mass, smaller maps correspond to high frequency, and that's why here in this region at high energy, we have the CH and H or AH vibrations. In a totally quantized atomic picture, we have energy levels associated to electronic transition that typically occur in the UVVs, then we have vibrational transition that occur in the infrared, and then we have rotations that occur in the microwaves. To carry out vibrational spectroscopy, we can directly excite the molecules by infrared light. So, vibrational spectroscopy can be performed in the infrared by a simple absorption experiment in which we have a multicolor light source, the sample, and the detector that detects what is transmitted at each energy. In the so-called infrared absorption spectroscopy, the electromagnetic field couples to the molecular dipole. This is given by this formula in which P is the dipole moment of the molecule and E is the incident field. What is the dipole moment? Let us assume that we have a molecule in which the charges are separated by some distance d, positive charges delta, negative charges delta. Then the dipole moment is a vector defined as the product of the charge times the displacement vector. For a polyatomic molecule, the dipole moment of the molecule will be the sum of the dipole moment associated to each charge. So we have to sum over all the charges, the charge position, that will be function of the normal coordinates if the nuclei move, and this formula will provide you with the final dipole moment that will depend on the normal coordinate qk. It is important to note that homonuclear diatomic molecules are typically non-polar because they are symmetric, so there is no net dipole moment. While in heteronuclear diatomics or asymmetric triatomic or polyatomic molecules typically have a permanent dipole moment, and this allows these molecules to couple more easily to the electric field. Infrared light couples to molecular vibrations only if they feature a changing electric dipole moment. So this means if the derivative with respect to the normal coordinate qk of the dipolar moment p, function of cube k, is different from 0. Modes that can be excited with infrared light are called infrared active, otherwise they are called infrared inactive. Let's see some examples. Let's consider the SO2 molecule. This is a 3-atomic non-linear molecule in which we have 3 different vibrational modes: symmetric stretch, asymmetric stretch, and some scissoring modes. As you can see, in this mode, the net dipolar moment changes with the normal coordinates, plus q equal to 0, minus q. So the mode is infrared active. As well, the asymmetric stretch is infrared active because, again, the dipolar moment, as you see here, changes with the vibration. The same holds for the scissoring mode. Let's now consider a CO2 molecule that is a linear molecule. As we can see here, this symmetric stretch has a zero dipole moment that does not change with the normal mode. So we expect that this mode is infrared inactive, cannot be excited with infrared light. Conversely, if we consider this bending mode, we see here that the dipole moment will change with respect to the normal coordinates, so we expect it to be infrared active, and this is what actually occurs. Infrared spectra are represented in terms of the transmitted radiation intensity versus the wave number of the incident radiation. Here we can see the absorption spectrum of the two methylpropanol molecules, in which we see the vibrational modes are as deeps, so the light is absorbed, so the intensity, the transmitted intensity detected, is smaller, and we see the most prominent absorption band that are the CO modes, and around 3000 centimeters to the minus 1, the CH modes. Two different approaches can be used to investigate vibrational energies. We have seen so far infrared spectroscopy, in which we investigate the light absorption in the infrared. But there is also another kind of spectroscopy, that is Raman spectroscopy, that is based on light scattering, with monochromatic sources exciting in the UV, vis, or near infrared. In this case, we have a laser source that shines a sample, and the scattered light is detected by a specific detector. To understand what Raman spectroscopy is, we have to introduce a new concept, the concept of polarizability, or induced dipole moment. When a molecule is placed in an electric field, electrons are separated from the nuclei, generating a dipole. We see here, we apply an electric field, the charges are separated. If we apply a time-varying field, we will have, as a result, an oscillating dipole. So we change from this configuration to this, in which the charges are opposite, as we see in this animated GIF. So we will have a dipole moment that will be somehow proportional to the time-varying electric field by a proportionality constant that is alpha. Alpha is actually not a constant, but is a tensor. It means a rank 2 tensor. And this is due to the fact that not necessarily the dipole moment must have the same orientation of the electric field. In normal Raman scattering, the polarizability tensor is a symmetric tensor, so the off-diagonal terms are equal. What is most important is that alpha is a function of the nuclei position. Alpha is a function of the normal coordinate qk for every k. And in particular, since the normal coordinate has an harmonic variation behavior, we expect something like that is an harmonic time dependence also from alpha. For small vibration, the polarizability tensor alpha can be developed into a Taylor series, as follows. So here we have alpha, that is a constant, alpha 0, plus the derivative of alpha with respect to the normal coordinate calculated at the equilibrium position, qk equal to qk0, times the oscillation amplitude times cos of omega kt. Let's consider an incident field oscillating at frequency omega photon impinging on a molecule in which the nuclei are vibrating at omega k. The incident field will induce an oscillating dipolar moment given by the scalar product of the polarizability tensor times the electric field. This will give rise to three components. It means that the light will be scattered at three different frequencies. The first one will be the same of the incident light, omega photon, and this is the so-called radial scattering. The molecule is just diffusing the incident photons at a different direction. But there are two other components, and these components do not have the same energy of the incident photon. One is the Raman Stokes photon that has a frequency that is smaller than the incident photon, by an amount equal to the energy of the vibrational mode, and another component that is the Raman anti-Stokes that has frequency higher than the incident photons, omega photon plus omega k, where again omega k is the energy of the vibration. So if we are able to detect these photons, we will have information on the vibrational energy. And this is the power of Raman spectroscopy, performing vibrational spectroscopy with scattered, by detecting the scattered light instead of the absorbed light. Raman spectra are presented by plotting the intensity of the Raman signal versus the wave number shift delta nu tilde. This is also called the Raman shift. The Raman shift is defined as the difference between the laser wave number nu tilde L and the Raman photon wave number nu tilde R. With this definition, the Raman shift is positive for Stokes photons and negative for anti-Stokes photons. The UPAC recommends that the Raman spectra must be plotted with abscissa linear in the wave number shift measured in centimeters to -1 and increased to the left. But this latter feature is rarely done. This plotted here is a typical Raman spectrum of CCl4. As we have seen in the previous slides, vibrations are quantized, so we see emission at discrete energies, in this case 218 centimeters to -1, 314, 459, 762 and 790. These on the left, at positive wave number shifts, are the Stokes bands. Symmetrically on the right, at negative wave number shifts, we have the anti-Stokes bands. You see here the positions are the same and are symmetric with respect to the Stokes bands. This we have already seen in the previous slide. At the center, at zero wave number shift, it means at the same wavelength of the excitation laser, we have the Rayleigh scattering, which is much more intense than the Raman Stokes or anti-Stokes. If you calculate the intensity of the Stokes, or equivalently of the anti-Stokes modes, we discover that this is proportional to the derivative of the polarizability tensor with respect to the normal coordinate. This means that light couples with molecular vibrations only if the molecular vibrations feature a change polarizability. So if the derivative of the polarizability tensor with respect to the normal coordinate is different from zero. This induces some selection rules that, as we will see, are complementary with respect to those observed in infrared spectroscopy. To better see this, let us focus on the CS2 molecule. CS2, like CO2, is a triatomic linear molecule that features 4 vibrations. One is the asymmetric stretching, one is the symmetric stretching, and 2 other degenerate modes are the bending, the delta bending at lower energy. As we have said before, in order to an infrared mode to be active, the dipole moment, or the derivative of the dipole moment with respect to the associated normal coordinates, must be different from zero. And this occurs, as we have seen for CO2, for the antisymmetric CS2 stretching and for the bending modes that, as we see in this plot, are infrared active. So we see the 2 peaks or the 2 dips of FTIR. For what concerns the Raman spectroscopy, in order to a mode to be active, the derivative with respect to the normal coordinates of at least one component of the polarizability tensor must be different from zero. Now let's see why these 2 modes are infrared active and are not Raman active, and why this mode is Raman active and not infrared active. Let's focus our attention on the antisymmetric mode. If we plot the polarizability versus the normal coordinates, we discovered that at the extrema, the polarizability has no change. So the derivative of the polarizability with respect to the normal coordinate calculated at these 2 points will be 0. As a consequence, this mode will be inactive. This is the same for this bending mode. Again, we have a dependence, a parabolic dependence of the polarizability with respect to the normal coordinate, and as well there is no net change between the polarizability in this position or in this position associated to this and this position of the normal coordinates. So since the net change is 0, the derivative is 0, and so this mode will be also Raman inactive. Let us consider this mode, that is the symmetric stretching. For the case of the symmetric stretching, we see that the polarizability increases, okay, or at least changes. And this means that the derivative of the polarizability at q equal to 0 is different from 0, and this means that this mode is Raman active, as we see here.